determine panel loading for both continuous and non-continuous duty motors, specifically for balancing the loads on the phases in an electrical panel, you'll want to reference the National Electrical Code, NEC. For continuous loading, you'll find relevant information in NEC section 430.52b5. This section dictates that for continuous duty motors, you must use the full load current, FLC, from table 430.250. For example, if you have a 2 horsepower, 3-phase 208 volts motor, the full load current per phase according to table 430.250 is 7.5 amps. To calculate the apparent power per phase, the formula is voltage multiplied by current multiplied by the power factor. In this case, it's 208 volts multiplied by 7.5 amps multiplied by 1, assuming a unity power factor, which equals 1.56 kilovolt amps. Therefore, for continuous loading, the panel loading would be 1.56 kilovolt amps per phase. Now, for non-continuous loading, refer to NEC section 430.52b4. This section covers motors with a service factor greater than 1.0 and specifies using 125% of the full load current from table 430.250. Since the NEC does not provide specific guidance for motors with a service factor of 1.0 or less, you can also use 125% of the full load current as a conservative estimate. If you have a motor with a service factor of 1.0, the full load current per phase is still 7.5 amps from table 430.250. However, you must adjust the full load current per phase by multiplying it by 1.25, which gives you 9.38 amps. The apparent power per phase is then calculated as 208 volts multiplied by 9.38 amps multiplied by 1, again assuming unity power factor. This equals 1.95 kilovolt amps. Therefore, for non-continuous loading, the panel loading would be 1.95 kilovolt amps per phase. So to recap, firstly, for continuous loads, use the full load current directly from NEC table 430.250 and calculate apparent power. Secondly, for non-continuous loads, increase the full load current from NEC table 430.250 by 25% and then calculate apparent power. These calculations help you determine the kilovolt amps per phase for balancing the load on your electrical panel and adhering to NEC requirements. When calculating motor loads for electrical panel balancing, it's essential to understand the distinction between continuous and non-continuous loading and how the National Electrical Code, NEC, addresses each scenario. Let's delve deeper into the nuances of these calculations, ensuring compliance and optimal panel performance. Firstly, continuous loading is defined as a load where the maximum current is expected to continue for 3 hours or more. According to NEC section 430.52b5 for continuous duty motors, the full load current, or FLC, from table 430.250 must be used. Table 430.250 provides the full load currents for motors based on their horsepower, voltage, and phase. To illustrate, consider a 5 horsepower, 3-phase, 480 volts motor. According to table 430.250, the FLC is 6.4 amps. To determine the apparent power per phase, which is a critical factor in panel balancing, the following formula is applied: voltage multiplied by current multiplied by the power factor. Assuming a unity power factor, which is a common simplification, the apparent power per phase is 480 volts multiplied by 6.4 amps multiplied by 1, resulting in 3.7 kilovolt amps. Therefore, for this continuous load, the panel loading would be 3.7 kilovolt amps per phase. Secondly, non-continuous loading applies to situations where the motor operates intermittently or for periods less than 3 hours. NEC section 430.52b4 addresses motors with a service factor greater than 1.0. The service factor indicates the motor's ability to handle brief overloads. For such motors, the NEC mandates using 125% of the FLC from table 430.250. However, the NEC provides no specific guidance for motors with a service factor of 1.0 or less. In these cases, adopting a conservative approach by also using 125% of the FLC is prudent. Let's consider a 10 horsepower, 3-phase, 208 volts motor with a service factor of 1.0. From table 430.250, the FLC is 28 amps. Applying the 125% adjustment, the adjusted FLC per phase becomes 1.25 multiplied by 28 amps, equaling 35 amps. Consequently, the apparent power per phase is calculated as 208 volts multiplied by 35 amps multiplied by 1, assuming a unity power factor, which yields 7.28 kilovolt amps. Thus, for this non-continuous load, the panel loading would be 7.28 kilovolt amps per phase. It's important to note that using a unity power factor simplifies the calculations, but in real-world scenarios, motors often operate with a power factor less than 1. To obtain a more accurate assessment of the apparent power, the actual power factor of the motor should be used. Motor nameplates typically provide the power factor information. Furthermore, the NEC provides guidelines on motor protection, including overcurrent protection and overload protection, which are essential for ensuring motor longevity and safety. These protection devices must be sized appropriately based on the motor's FLC and service factor. Additionally, it's crucial to consider the ambient temperature and motor enclosure type when selecting conductors and protection devices, as these factors can affect their ampacity and performance. For instance, conductors installed in high ambient temperature environments may require dirting to prevent overheating. In summary, accurately calculating motor loads for electrical panel balancing involves firstly, distinguishing between continuous and non-continuous loading, secondly, utilizing the appropriate FLC from NEC Table 430.250, thirdly, applying service factors and NEC guidelines, and fourthly, considering the motor's power factor and protection requirements. By adhering to these principles, electrical professionals can ensure compliant and efficient panel designs. Moreover, understanding the NEC requirements and applying them correctly is essential for ensuring electrical safety and code compliance. Regular reviews and updates of your knowledge are recommended to stay abreast of any changes in the NEC. Also, consulting with a qualified electrical engineer or inspector can provide valuable insights and guidance, particularly for complex or critical applications. Remember that accurate calculations and proper implementation are paramount for maintaining a safe and reliable electrical system. Let's delve further into the practical implications and detailed considerations when calculating motor loads for electrical panel balancing, emphasizing compliance with the National Electrical Code (NEC). Firstly, it's vital to differentiate between continuous and non-continuous loads correctly. Continuous loads, as defined earlier, operate at their maximum current for 3 hours or more. Identifying these loads accurately is essential because they require different treatment under the NEC compared to non-continuous loads. Secondly, when using NEC Table 430.250 to determine the full load current, FLC, ensure you are referencing the correct table and values based on the motor's voltage, phase, and horsepower rating. Using the wrong values can lead to inaccurate calculations and potentially undersized conductors or overcurrent protection devices. Thirdly, the service factor plays a crucial role in determining the adjusted FLC for non-continuous loads. Motors with a service factor greater than 1.0 are designed to handle temporary overloads without overheating. As per NEC section 430.52b4, these motors require using 125% of the FLC from table 430.250. However, for motors with a service factor of 1.0 or less, although the NEC doesn't explicitly state the requirement, it's a conservative and recommended practice to also use 125% of the FLC. Fourthly, the power factor of the motor should be taken into account for a more precise calculation of the apparent power. Assuming a unity power factor simplifies the calculations, but it may not accurately reflect the real-world scenario. The motor's nameplate usually indicates the power factor, which can be used in the apparent power formula: voltage multiplied by current multiplied by the power factor. Ignoring the power factor can lead to an underestimation of the actual load and potential issues with voltage drop and system efficiency. Fifthly, consider the impact of conductor ampacity and temperature correction factors. The NEC provides tables that specify the ampacity of conductors based on their size, insulation type, and installation method. However, the ampacity may need to be adjusted based on the ambient temperature and the number of current-carrying conductors in a raceway or cable. These temperature correction and derating factors are essential to ensure that the conductors can safely carry the calculated load current without overheating or causing insulation damage. Sixthly, the overcurrent protection and overload protection for the motor must be properly sized and coordinated. The NEC provides guidelines for selecting the appropriate fuses or circuit breakers to protect the motor and conductors from overcurrents and short circuits. Overload protection devices, such as thermal overloads or electronic motor protectors, are designed to protect the motor from sustained overloads that can cause overheating and damage. The selection and sizing of these protection devices must be based on the motor's FLC, service factor, and other relevant factors. Seventhly, voltage drop calculations are crucial for ensuring that the motor receives adequate voltage under load conditions. Excessive voltage drop can lead to reduced motor performance, overheating, and premature failure. The NEC recommends limiting voltage drop to a maximum of 5% from the source to the motor terminals. Voltage drop calculations should be performed based on the calculated load current, conductor length, and conductor size. Finally, proper documentation and labeling are essential for maintaining a safe and well-organized electrical system. All motor circuits and panels should be clearly labeled with the motor's nameplate information, calculated load current, conductor size, and overcurrent protection device rating. This information can help facilitate troubleshooting, maintenance, and future modifications. In summary, calculating motor loads for electrical panel balancing requires firstly, a thorough understanding of the NEC requirements, secondly, accurate data collection, thirdly, precise calculations, and fourthly, careful consideration of various factors such as service factor, power factor, conductor ampacity, and protection devices. By following these guidelines, electrical professionals can ensure safe, compliant, and efficient electrical systems. To further elaborate on the nuances of calculating motor loads for electrical panel balancing, let's explore several specific aspects and considerations. Firstly, harmonics in motor loads can significantly impact electrical panel loading and system performance. Harmonics are non-sinusoidal currents and voltages that can be generated by electronic devices, including variable frequency drives, used with motors. These harmonics can cause increased heating in conductors, transformers, and other electrical equipment, as well as distortion of the voltage waveform. When calculating motor loads, it's essential to consider the potential presence of harmonics and their impact on the overall system loading. This may involve using harmonic filters or other mitigation techniques to reduce the harmonic distortion. Secondly, the type of motor starter used can affect the inrush current drawn by the motor during startup. Motor starters are used to limit the inrush current and provide overload protection for the motor. Different types of motor starters, such as across-the-line starters, reduced voltage starters, and soft starters, have different inrush current characteristics. When calculating motor loads, it's important to consider the inrush current of the motor and ensure that the electrical panel and conductors are adequately sized to handle this current without causing excessive voltage drop or tripping of overcurrent protection devices. Thirdly, the ambient temperature can significantly affect the ampacity of conductors and the performance of electrical equipment. The NEC provides tables that specify the ampacity of conductors based on their insulation type and installation method. However, these ampacities are based on a specific ambient temperature, typically 30 degrees Celsius. If the ambient temperature is higher than this, the conductor ampacity must be derated to prevent overheating. Similarly, the performance of electrical equipment, such as circuit breakers and transformers, can be affected by high ambient temperatures. When calculating motor loads, it's important to consider the ambient temperature and apply appropriate temperature correction factors to ensure that the conductors and equipment are adequately sized. Fourthly, the altitude at which the electrical system is installed can also affect the performance of electrical equipment. At higher altitudes, the air is less dense, which can reduce the cooling effectiveness of electrical equipment. This can lead to overheating and reduced performance. When calculating motor loads for systems installed at high altitudes, it's important to consider the altitude and apply appropriate correction factors to ensure that the equipment is adequately sized. Fifthly, the presence of other loads on the same electrical panel can affect the motor load calculations. Electrical panels typically serve multiple loads, including lighting, receptacles, and other equipment. When calculating motor loads, it's important to consider the other loads on the panel and their impact on the overall loading. This may involve performing a load calculation to determine the total demand of the panel and ensure that the panel is adequately sized to handle all of the loads. Sixthly, the future expansion of the electrical system should be considered when calculating motor loads. Electrical systems are often designed to accommodate future growth and expansion. When calculating motor loads, it's important to consider the potential for future motor additions and ensure that the electrical panel and conductors are adequately sized to handle these future loads. This may involve oversizing the panel and conductors to provide additional capacity for future expansion. Finally, regular maintenance and inspection of the electrical system are essential for ensuring its continued safe and reliable operation. Electrical systems should be inspected regularly to identify any potential problems such as loose connections, damaged conductors, or overloaded circuits. Maintenance should be performed as needed to correct any identified problems and ensure that the system is operating properly. In summary, calculating motor loads for electrical power balancing involves firstly, considering the effects of harmonics, secondly, accounting for motor starter types, thirdly, adjusting for ambient temperature and altitude, fourthly, analyzing the impact of other loads, fifthly, planning for future expansion, and sixthly, maintaining regular maintenance and inspections.